Okay, great. Thank you for the invitation. As I was saying, I'm actually very happy to be here because the last time I was here, one of the organizers of this school was a student in this winter school. So, and hint, it wasn't Dimitri or Pierce. So I think the next time I come, it's reasonable to expect that one of you will be co-organizing. So that's great. Okay, so the title of my talk is slightly changed because as I wrote my talk, it became clearer what I would be talking about. And what I'm talking about is slightly more broader than the title. It's duality of strongly coupled theories in 2+1 dimensions. And I should acknowledge that I sort of developed these things with a couple of collaborators, Mike Mulligan, who's now a professor at UC Riverside, and an extremely talented postdoc at Stanford, Jingyuan Chen, as well as several students with whom I've enjoyed discussing, shown here. Okay, so the subject is quite elegant and beautiful, and for many of us, that may be motivation itself, but I should start by telling you how I got interested in the subject. Of course, I like beautiful theoretical physics, but ultimately, I find satisfying to make contact with experiments. And I sort of got into this subject from a phenomenological point of view. About 5 years ago, I decided that the progress I was making on quantum criticality in materials was quite far from making contact with experiment. And I come to the conclusion that the most likely system in which quantum criticality is manifest that I have a chance of coming close to explaining experimentally, the experimental observations, were two quantum critical phenomena, two sets of quantum critical phenomena in 2+1 dimensions. And they both have the common feature that they involve the interplay of strongly interacting degrees of freedom, quench randomness, and two-dimensional systems. So the first example is a magnetic field-tuned superconductor to insulator transition. I should say these transitions have been viewed, perhaps incorrectly, as being more difficult than the metallic critical points that you heard about yesterday. But I claim that we have a greater chance of making contact with these than the much harder problem that we should try to make contact with strongly correlated materials. So the first example of such transition is a magnetic field-tuned superconductor to insulator transition. Let's just see if there's a pointer. Is there a pointer here? No? No, that's fine. Is there a stick?
They have a pointer. I know it's a desk.
That's okay. I'll just. The phase diagram in 2 dimensions is you have a zero-temperature superconductor. Thank you so much. And you apply a magnetic field. You destroy superconductivity. And you go into an insulating state. Okay? And this red dot is the superconductor to insulator transition tuned by a magnetic field. The second experiment that I was motivated by is, again, a 2-dimensional system, a 2D electron gas in a strong perpendicular magnetic field. And this undergoes a quantum Hall to insulator transition. So again, at 0 temperature, you have a phase of matter known as the integer quantum Hall effect, say. You apply a magnetic field, eventually you destroy the quantum Hall effect, and the system becomes an insulator. And this transition is known as the quantum Hall to insulator transition. So if you look at the experimental data, you see several striking features. Here is the field-tuned superconductor insulator transition. Perhaps you can't quite see what these different colors mean. They represent isotherms. So this is resistance as a function of magnetic field at a fixed temperature. Each of these are at different temperatures. So on this side, at high magnetic fields, temperature decreases down. So let's see, the other way around. As temperature decreases, the resistance increases. Sorry. And that's the insulating behavior. And on this side, as temperature decreases, the resistance decreases, and that's the superconductor. Okay? And where these isotherms cross, the resistance seems to be universal, and roughly the quantum of resistance of particles with charge 2e. This is the superconductor to insulator transition. In a similar way, you have the quantum Hall effect, where you apply a strong perpendicular magnetic field. Here I show you the resistivity, the longitudinal resistivity in the quantum Hall effect. Again, these are isotherms. As you lower the temperature, the resistivity decreases, because in the quantum Hall effect, the longitudinal resistivity, by definition, vanishes at 0 temperature, and the Hall resistance is quantized. Resistivity is quantized. So the dashed line represents the Hall resistivity. The solid lines represent the longitudinal resistivities. And on the quantum Hall effect side, the longitudinal resistivity decreases with temperature. On the insulator side, the longitudinal resistivity increases with temperature. And the isotherms, again, cross at this quantum Hall to insulator transition, where the resistance is roughly, but not exactly, the quantum of resistance now of charge E particles, okay? 26 kiloohms.
If you look at the large ensemble of systems which show SAT, how universal is the resistivity?
It's a very good question. I will show you the data. Yeah, yeah. Yeah.
When you apply the transverse field,
Mm-hmm.
what are you coupling to? You're not coupling to orbital motion. You're not coupling to spins either, because they're spin polarized. What are you coupling to?
Well, you have Landau levels, right? So as you increase the magnetic field, you increase the number of states that the Landau level accommodates.
You were tuning the transverse field, not the perpendicular field.
Perpendicular field. This is perpendicular field.
Oh, okay.
Yeah. Sorry if I was being unclear. Transverse meaning perpendicular. Well, I always get confused with longitudinal versus transverse. Okay. All right, so several striking features are exhibited by these two transitions. Some of them are universal to all quantum critical points. The first is the notion of dynamic scaling. So when you tune some parameter towards a phase transition, there's a length scale that diverges, and that's called the correlation length. And I denote that by xi. And here the tuning parameter is the magnetic field. But in quantum critical phenomena, the time scale associated with imaginary time, so the characteristic time scale also diverges, but that affects thermodynamics. And the relationship with the way time scales diverge relative to length scales is given by another critical exponent, which we denote z, and that's the dynamical exponent. So if you use simple reasoning, like, for instance, quantum mechanical reasoning, that a characteristic frequency is related to an inverse of a characteristic time, and hence, and also a characteristic energy is related to a characteristic frequency. Lastly, that a temperature has units of energy, so that should go as the inverse of some time scale. You can find that you can express temperatures in terms of near the critical point characteristic inverse time scales. Okay? So if you make a measurement at magnetic field and a temperature, you can express the magnetic field in terms of the correlation length, the temperature in terms of the inverse correlation time. And what you expect is that resistivity as a function of magnetic field and temperature should be some number, which I denote rho star, times a function of dimensionless arguments, the ratios obtained from extracting the magnetic field and the temperature dependence. And so this delta is the tuning parameter, and t is the exponent is 1 over nu z, and it comes from these arguments, just dimensional analysis. If you want to know more about this, you can ask me anytime. Then there's so that tells you, if you now take your data and collapse it, that gives you an indication of what nu z should be. Now, you can also do nonlinear current voltage measurements and express the electric fields that you measure and the energy associated with an electric field. So near the critical point, the energy associated with an electric field is Q times the electric field times the length. And near the critical point, that length will be the correlation length, so that can be expressed in terms of the field. And furthermore, that electric energy is an energy, so it can be expressed in terms of this inverse correlation time. So when you put it all together, you find that the nonlinear IV curves as a function of electric field and temperature should be some function g divided by delta over this scaling function. The punchline is that from these two measurements, the first measurement gives you one critical exponent, nu z, and the second exponent gives you nu independently of z. So with these two experiments, you can obtain two critical exponents, nu and z. And to the extent that we rigorously accept what we see in experiments, the conclusion from such analysis is that for the field-tuned superconductor insulator transitions, nu is roughly 2.3, z is equal to 1, and I'll address your comment in a second. The critical resistance is h over 2e squared, and the critical Hall resistivity is 0. For the quantum Hall effect, you get the same nu, the same z. Rho xx is approximately the quantum of resistance of electrons, and rho xy is also the quantum of resistance of electrons.
So these are statements from the data?
From the data, yes, yes. Now, if you want to construct a theory of this data, our favorite type of theory is based on free particles, harmonic oscillators, perturbation theory. If you take a strict non-interacting description of both of these transitions, you will not succeed. Okay? Now that's actually surprising to many people when I mention this, because we all think of the integer quantum Hall effect, for instance, as a free electron system. Certainly not a fractional quantum Hall effect. The insulator is a free system, so why would the critical point be not free? Well, just because two phases of matter are governed by free fermions doesn't mean the critical point between them is always free. Yeah, you had a question?
Yeah, so you had mentioned that you introduced this z because you've gone to imaginary time, so you pick up this dynamical exponent. But z winds up being almost 1, so what does that imply as to the relationship between those two statements? Because now z is not just a constant, but it's unity. So then these two correlations are the same?
Near the critical point, the rate at which a time scale diverges and a length diverges is the same. But in general, they shouldn't be the same. Condensed matter systems are not Lorentz invariant, so you expect different behavior. It's sort of surprising that you actually see this. And this, I may not get to it, but z equals 1 doesn't imply Lorentz invariance, actually. It turns out in this case it's not Lorentz invariant, even though z is 1. Okay, so then you can look at the data and you say, how are these? There seem to be some similarities. Some critical exponents, if you accept that, are the same. How are these two quantum critical points related? And can we construct an approximate calculational framework for obtaining the critical resistivities, these rho stars, and these critical exponents? So that really was what motivated me to get into the subject that I'm going to lecture to you about today. Yeah.
So are these transitions occurring at fixed particle density?
Yes. Yes. You can apply a gate voltage, but the experiments that I'm talking about now, you work at fixed density. The magnetic field is being the tuning parameter.
And this quantum Hall transitions at high Lambda level or low Lambda level?
So the data that I showed, for instance, was the nu equals 1, the integer, one Landau level was filled, and then it was depleted. Okay, but similar observations have been made in higher Landau levels as well. Okay?
What about fractional?
There's been some work on fractional. Actually, even here, microwave absorption has been done in the fractional quantum Hall effect as well.
And does it also fit into this paradigm?
The resistivities, the critical resistivities are different, but to the extent that they've been studied, the critical exponents seem to be the same. Yeah. Okay, so now to address this point about how universal is the quote-unquote universal resistance for the field-tuned superconductor to insulator transition. Okay, so what you are seeing here is these are data from many different types of materials that undergo the superconductor insulator transition. One class of materials undergo, so what this HC2 represents is the magnetic field at which you lose the superconductivity. Okay? One set of materials undergo this superconductor to insulator transition where the critical conductance is 4e squared over h, so the critical resistance would be h over 4e squared. Then there's another class which is totally different than this, exhibiting this universal resistance, but the claim is that they don't undergo a superconductor to insulator transition, but they actually undergo a superconductor to metal transition, and I don't understand those at all. I'm focusing down here. Okay? So the extent to which it's universal, if you look at this data at face value, it's not, because if you're in this region, it's not at this region.
Yeah, you need to know where to kind of limit your
Absolutely.
selecting class.
Absolutely.
But what if you tune the superconducting insulator at transition
In zero field?
by disorder?
Yeah, in a zero field,
Yeah.
it's totally different than this number. Yeah. And people have simulated that in quantum Monte Carlo and get, to the extent that you can do the analytic continuation, some different numbers as well. So those are completely different theories, in my opinion. One involves field-induced vortices and one doesn't.
So how clear these samples on this line, those insulator transitions?
In this region, if you look at temperatures above the superconducting TC, the resistance is roughly of the order of the quantum of resistance of electrons. So they're pretty dirty films. Out here, they're not. They're somewhat cleaner. Yes. Okay, so that's the phenomenology. And what I probably won't get to, since I want to actually talk about the pure theoretical physics, but my own interest in thinking about these two problems, I just want to summarize where I'm at. So if you include some of the ideas that I'll discuss with you today, duality ideas with inclusion of quench disorder, what we can do is we can see how these two quantum phase transitions are relatable to one another. That's one thing. We can obtain the critical resistivities, and we can show that Z is 1. Okay? But we're still working on this correlation length exponent nu. Okay? So that's where I'm currently. That's the status of my work on this. Now, this is not the only motivation to study the subject. There's many other motivations. For instance, there's aspects of deconfined quantum criticality if you don't have disorder. You can study physics of surface states of strongly coupled topological insulators and try to make contact with certain quantum spin liquid states. For that more broader perspective, which is very helpful, I recommend this beautiful review that was recently posted last year. And it's a very pedagogical treatment of the subject. Okay, so now let me actually get to the pure theoretical parts of these lectures. Okay, that was the motivation. The first part I'm going to talk about is just general ideas of what duality is and how one incorporates them in our thinking. Then I will specialize to 2+1 dimensions. I'll talk about two types of dualities. One is boson-vortex duality, and one is boson-fermion duality. Then, as I go on, these are members of a broader web known as the duality web, and I'll talk about that. And finally, if time permits, I'll come back to the experimental questions that I alluded to just so far. Now, I'm firmly of view that when you do theoretical physics, you might be inspired by experiment, but you write down a model and seriously solve it, and then worry about making contact to experiment. So what I should say, since this is a school, what is true and what is speculation? The first three parts of this talk are true, as far as for a physicist, maybe not for a mathematician. And then the last part is work in progress speculation, possibly fake news, but I'm not sure. Okay? Okay. So for the first part, and are there questions or? Okay. So here's my motivational invitation to study duality in general as a problem of theoretical physics. So we all know this beautiful classic model of the 2D Ising model. It's basically spins take a square lattice, classical binary numbers, which are plus or minus 1. And this undergoes a second-order phase transition at finite temperature in 2 dimensions at some temperature Tc. Now, as you approach the critical temperature from above, you can look at the correlation length of these spins, and the correlations diverge exponentially. Okay? And the rate at which they diverge, the characteristic length scale, is the correlation length. And this correlation length diverges as the temperature approaches Tc. Okay? So this is what you would study in a course in critical phenomena. Now, this is an exactly solvable model, so we know what the correlation length exponent is. It's 1. Okay? Now, if we do our favorite approximation, namely mean field theory, you get a half. Okay? Then you can perturb about mean field theory using Feynman diagram methodologies and perturbative renormalization group techniques. And you get 1/2 plus a small number, epsilon. And epsilon is similar to the epsilons you've heard in this week. It's namely a deviation from 4 dimensions where mean field theory is applicable. So you can increasingly try to work harder and harder. There's many, many more diagrams, the factorial number of diagrams at higher order. And then you quickly lose the ability to make contact with this exact result. So instead, what you might try to do is try to abandon the perturbative approach and think about it in a different way. Okay. Now, this may sound like I'm downplaying perturbation theory. I actually happen to love perturbation theory and diagrammatic perturbation theory. It's just about finding the right coordinates in which to do it. Okay? So that's one of the themes that in the later part of my talk will be, if you do perturbation theory in the wrong coordinates, you're going to be far away from truth. But if you do it in the right coordinates, you get a little bit closer if you're lucky. Okay? So instead of doing it this way, let's do it a slightly different way. There's many ways of seeing it. One of my favorite ways of seeing it is, so if you study the problem of quantum critical phenomena, you realize that a quantum problem in d dimensions can be related to a classical statistical mechanics problem in d+1 dimensions. And in this case, the Ising model, classical Ising model in 2D, maps onto a 1D quantum Ising chain, where you have now, these are quantum operators, Sx and Sz. They have an Ising exchange plus a field that's perpendicular to the z direction. That's the transverse field G. Okay? So this is the classical to quantum mapping. I'm not deriving anything in these lectures. I want you to get a sense of what can be done rather than what is done. And if you want to know more, you can read the relevant literature. So now from these spin models, you can map onto fermions using what's called a Jordan-Wigner mapping. And when you do that, you find that the Ising model is related to some hopping problem of fermions in the presence of superconductivity, as shown by this second operator. And after all is said and done, this is a free fermion problem now, much easier to do things, because it's a quadratic theory. You simply diagonalize the matrix using a Bogoliubov transformation, just like you do in the theory of superconductivity. And you find that the energies, the spectrum, is basically Lorentz invariant. There's a mass scale, and then there's the speed of light with some dispersion. And these operators are the eigenoperators of the spectrum. Okay? And you can then go back and relate how the transition temperature of the original classical Ising model is related to the parameters of this fermionic problem. What's the fermion doing? It's doing some subtle phase transition where the symmetry is not changing, but the topology is changing. And I won't go into that unless someone wants me to do that. But let's just take this at face value. You can relate the deviation from Tc to the mass of this fermion. Okay? And the mass, in turn, the correlation length, in turn, is related to the Compton wavelength of this particle, which, as you remember, the Compton wavelength is 1 over h bar over mc, right? So because the correlation length goes like 1 over the mass and the deviation from criticality goes like the mass, you can immediately see from this that nu is 1.
So these are all transformations on the Hamiltonian, which takes you from the original 2D Ising all the way to the effective model of free fermions. How does temperature get into the Hamiltonian?
Because temperature is in the classical problem can be related to the tuning parameter of the quantum critical transition.
So it's not a canonical.
Correct. You have to think about it in terms of transfer matrices. Exactly. Yes. All right, so this mapping that I was using, which is known as the Jordan-Wigner mapping, relates Pauli matrices to spinless fermions. And it's given like this. And one of the reason I show you this is because this is a simple example of a duality transformation relating 1D Hamiltonians. Once you go to the transverse field Ising Hamiltonian, you can then dualize at the level of the Hamiltonian. And the key take-home message so far is that you know, these are local operators. The fermions are local operators, but the relationship between them is non-local. Non-local relationship between spins and fermions, because the Pauli matrix at site I depends on these fermions at all j less than I. Okay, so now there's another example of duality, which involves the XY model. So those are spins, easy plane spins on the lattice. And this we can construct at the level of partition function duality. And it turns out to be dual to a Coulomb gas of vortices. Okay? And this little e denotes a fictitious electric field, which is the electrostatic energy, if you remember from freshman physics. The electrostatic energy, and this is some dielectric constant. The electric field lives on links of some lattice, some dual lattice. The electric field is constrained by Gauss's law that says that the divergence of it at every lattice site is given by the vortex vorticity, n sub v. Okay. This was not how it's derived in these classic papers that I show down here. These are really worth reading, especially this paper in blue. But instead, let me cut to the chase and put it this way. If you really understand a problem, you can tell a computer how to solve things, right? So if I ask, let's simulate the XY model, we know how to simulate this in classical Monte Carlo. You simply try to change the angles and accept with some weight. Now, if you want to work in the dual representation, you can do the same thing. And what you can do is you have some lattice with electric fields on the links. And what you can do is try to do two types of things. You want to preserve this constraint at every point of the simulation, right? So you can create a vortex-anti-vortex pair, which is like a plus-minus charge. But then to preserve Gauss's law, there must be some electric flux coming out. Okay? That's one type of move. And then there's another one which has no charge involved, where you just have a plaquette with some electric field running through it. And that's another excitation in the system weighted by this Hamiltonian. So if you do that just by classical Monte Carlo, you can observe the Kosterlitz-Thouless transition, which is this famous transition exhibited by the 2D XY model. Okay? And the way you see this is that there's a universal jump of the superfluid density. This was noted from studies of the Kosterlitz-Thouless transition. In the dual representation, what it manifests itself as is the change in the dielectric constant due to local screening by vortex-anti-vortex fluctuations. As the vortices at low temperatures, they're tightly bound, and the dielectric constant is some number set by the low temperature limit. At high temperature, you have a plasma of mobile vortex-anti-vortex pairs. There's no dielectric screening, and the jump in this is how we can characterize the Kosterlitz-Thouless transition in the dual representation. So the punchline is that the XY model is dual to an electrostatic problem in two space dimensions. Yes? Yeah?
Is it local under that transformation?
So, you know, to go from these variables to the vortex variables, these are essentially vortex variables because this is the electric field of a vortex, not in the lab. There's a non-local transformation because, again, if you have a vortex somewhere, the phases have to wind globally all around it by 2 pi everywhere. So there's a non-local relationship. Okay. And this non-local relationship is the first example of what I'll call what we call particle-vortex duality. So on one side, you have a vortex. In the representation of the XY model, you have currents. These are the vector fields of currents going around the vortex. And the currents are related to the gradients of the phase angles. Okay? Now, what you can do is if you simply rotate every arrow by 90 degrees, say, clockwise, you see that the circulation becomes a divergence. And this becomes now like the electrostatic problem of a charge with radiating electric fields. And this can be made explicit by looking at the fact that you can define a dual electric field Ex, which is the grad y of this phase degree freedom, the current in the y, and Ey is minus in the current in the x. So we know what a vortex is in the original representation. It's when the phase gradients wind by 2 pi. Right? In the dual representation, it's when the divergence of this electric field is 2 pi. So that's the Gauss law constraint. Okay? So these types of non-local transformations from one thinking to another can be thought of, is what I mean by duality. And from a sort of philosophical point of view, it's a severe blow to this ancient Greek idea of reductionism. So, but the Greeks believed that you take something, you break it up into small enough parts, you understand the parts, then you understand the thing. But here, there's, depending on who you are, you might like the XY model, but you might also like the vortices. They're equally fundamental to you. There's just, the relationship between them is just a change in coordinates. Another important take-home lesson from this is that the microscopic model doesn't always suggest what the best coordinates are. And that's an important lesson to take into mind. I think Andy crucially emphasized this in his talks. So if you're interested in long wavelength, low energy physics, you start with some microscopic model of electrons, say, if you're thinking of the quantum Hall effect, electrons in a big magnetic field with disorder, Coulomb interactions. It seems like a hopeless problem, but maybe you can work in a different set of coordinates where things look simpler. Okay? So with that general preamble, I'm going to talk about abelian dualities of strongly coupled systems in 2+1 dimensions. And if time permits, which it may not, their applications. Yes, only there'll be gauge theories with abelian gauge fields. No. Oh, okay, yeah. Right. Okay, so now we're on the next part of my talk. Okay, now we're going to go from 2D classical to 2D quantum, or 2+1 dimensions. Are there questions so far?
So when you say no fundamental particles in,
Yeah.
you mean no fundamental particles in condensed matter or in high energy?
Both. Condensed matter physicists have an open-minded view of things, right? So.
I understand. Would you do that the same for high energy?
Sure, I think all systems are condensed matter systems. So. Okay. In 2+1 dimensions, I will talk about particle vortex dualities. They will involve both bosons and fermions. And then I'll talk about boson-fermion duality. And there's some remarkable progress that has come to fruition recently that show that both of these are members of a larger web of dualities. And I'll discuss that web in the second part of my second lecture. Okay, so we said that the XY model is dual to electrostatics. By electrostatics, I mean that there's no photon, right? There's no magnetic field to cause waves to propagate. All of that is done with, if you wish. But in 2+1 dimensions, the XY model will be dual to electrodynamics, which means that there is a propagating photon-like variable. And the way you see that is if you have a 2D system, this is a two space dimensions. So you remember when you studied electrodynamics, there are these TE and TM modes, something like that. If you have a propagation in plane, that's K, the electric field and magnetic field must be perpendicular. This is a bad artistic representation of 90 degrees. But anyway, the electric field, if the electric field is in plane, the magnetic field will be perpendicular, right? So you can have electric fields in the plane, EX and EY, and a magnetic field perpendicular, BZ. Okay, so this is exactly the number of degrees of freedom of a current in 2+1 dimensions. There's the density and the current in the X direction, and the current in the Y direction. So we can relate the currents to these electric and magnetic fields. And so I always use lowercase symbols to denote the dual variables. So if you start with bosons in the lab, so like they could be superfluid degrees of freedom, their currents, Jx and Jy, I use capital letters. And you can express them, just as in the classical XY model, this last line was not present, you can express them in terms of the dual electric field. But now the density will be a dual magnetic field. And now when you have both electric and magnetic fields, you can have a propagating photon. Notice that if you have charge conservation, there's an equation of continuity. The time derivative of the density plus the divergence of the currents is 0. That is equivalent to the Faraday's law of induction, right? The dB dt is going to be like curl of E. So Maxwell's equations encode current conservation. That's how this thing works. Now, instead of writing it like this, there's a more compact way to express this condition in terms expressing the electric and magnetic fields in terms of a dual fluctuating gauge field, little a. So epsilon is the usual antisymmetric tensor. You write J mu is epsilon mu nu lambda, partial nu a lambda. For instance, if mu were 0, right, that means time, the density, then this becomes a curl, spatial curl, and that's a magnetic field. The 1 over 2 pi is just convention. Okay? So this vector field will capture the behavior of the photon, the dual photon. Okay? Questions? So this can actually be, you can go beyond this casual discussion and go and explicitly map the 3D XY model. You can start with a cubic lattice where you have angles living on the sites of the cubic lattice. You could couple the system to a vector potential. And capital A denotes actual vector potential, say, that you might apply in the laboratory. Okay? And they would live on the links of this lattice. And if you wanted to study the XY model, say on a computer, you would study the partition function by integrating over these phase variables. When I use capital letters and don't integrate over them, sometimes we call those background fields. That means the partition function depends on it, but we don't path integrate over it. Right? So notice the path integral does not have a, big A. Now, this model, after doing a set of almost exact transformations, I say almost because you have to do what's called a Villain representation of the cosine. You write the cosine in terms of a bunch of periodic parabola, but you still preserve the essential physics. And then you can go on and map this onto a new XY model with different fields phi. And now these variables live on the sites of a dual lattice, the dual interpenetrating lattice of this cube, which is another cubic lattice. And it has a different coupling. And the way it knows about the external field capital A is through the coupling of capital A through to the curl of little a. Notice that there's a new gauge field, little a, that this dual XY model talks to. Okay? So this little a, by contrast with the big A, is path integrated over. It's a dynamical variable. So the partition function of the original XY model can be expressed in vortex coordinates. This is the vortex representation, which is another XY model that couples to a dynamical gauge field. And that dynamical gauge field's flux couples to the background vector potential, A. And this term here is denoted here in the lattice. So the original lattice, the links of that, is where capital A lives. And the plaquette of the dual lattice is where the curl of little a lives. And the coupling between these two is local. Okay? And this was shown by Peskin and by Dasgupta and Halperin a long time ago. Sorry, delta is the lattice difference operators. It's the analog of a gradient, but on the lattice. Yeah, it's a vector. All right, so now this is the lattice version of this. But if you're close, oh yeah, please. Yeah. Little a is exactly these things back here that I talked about. So the currents of the original XY model can be expressed in terms of the gauge fields, some dual gauge fields. They're dynamical variables. I can put it in a different way. We know that vortices have long-range forces with one another, right? So if you take a two-dimensional system, there might be logarithmic interactions between vortices. What mediates those forces? It's that photon. Okay? So the long wavelength fluctuations of the current vector, the Goldstone modes, can be represented as the photon of this dual gauge field. And I'll make that more precise as we go along. But right now, it's just some exact mathematical operation. Okay? So what you do is you find that you can, when you do this on the lattice or in the continuum, you integrate over the angles theta, and that puts a constraint on the currents to be divergenceless. So if the current is divergenceless, it can be expressed as the curl of something in 2 + 1 dimensions. That something will be this little a. Okay? You'll see in a minute. Okay, so this is the lattice. Now, you can put this on a lattice and go in the vicinity of the phase transition where there's one parameter scaling, there's a length scale that's large. And so in the vicinity of that transition, you could think of this in terms of a continuum representation, like a Ginzburg-Landau framework. And the original XY model is exactly like the Ginzburg-Landau theory of a superfluid or superconductor. And that's given by this sort of, actually it's Ginzburg-Landau-Wilson, because this is a 2 + 1 dimensional action rather than a free energy. Okay? So this capital psi is the order parameter, and it has an amplitude and a phase. This theta was the thing that entered the XY model on the lattice. Okay? It has a tuning parameter to the phase transition, some interactions, et cetera, et cetera. The dots represent all the other terms that you could inherit from the lattice model, but which are unimportant, or in the RG sense, irrelevant near the phase transition. Now this duality that I described is as follows. So the dual theory involving the vortex degrees of freedom involves another field, lowercase psi, which is also a complex number. It has an amplitude and a phase, which I'll denote by phi. Those are the things that live on the dual lattice. And it also has a Ginzburg-Landau form, except now the covariant derivative, I should have defined this. This capital D sub A is a covariant derivative using the capital A. And this is a covariant derivative using lowercase a. Okay? So these sets of degrees of freedom couple to a fluctuating vector potential. The vector potential, in turn, couples to the background potential through this term. Okay? Now you can see from this, we know from how, if you have a Lagrangian, how do you define the current? Well, you differentiate it, functional differentiate it with respect to the external A. So when you do this, you find that the current is just epsilon mu nu lambda partial nu A lambda. That's exactly what we pictorially described before. The currents are related to these dual gauge fields, and that's encoded in the action. So, well, in the first part is just the definition of what the current is. If you differentiate with respect to big A, that's the currents. And the second one says that the duality says you could differentiate either, you should get the same answer, otherwise they won't be dual. Right? So the equality comes when you say the current is equal to this. Yeah, yeah.
If you try this in higher dimensions,
Uh-huh.
you get some gauge field with more indices. Or can you do it?
Well, this particular type of duality can be inherited from a higher duality, which I'm not going to talk about. It's this electric-magnetic duality. But that's a totally different thing. So if you imagine this to be in the surface of some bulk system, which has electric and magnetic duality, roughly speaking, there are two particles. There's the charges, charge E, and monopoles with charge 1 over E, 2 pi over E from Dirac's quantization. And one particle is like the original boson, and the magnetic particle is roughly like the vortex. Okay. What? Oh, that's what you're asking. Yeah. Okay.
Question?
Yeah, yeah.
Is there also a relation between little psi and big psi, like duality?
Well, so little psi is the vortex of big psi. And so the relationship, like the Jordan-Wigner mapping, is highly non-local. Right? Little psi and big psi are non-locally related. But actually, it turns out that psi squared is a local object, and that can be related to one another. The mass squared of one boson is related to the mass squared of the other. The reason for that is because if we look at the phase diagram, if we just knew about the XY model, right? There's two phases. Am I already done with time? Okay. All right. Okay. All right. I guess I went much slower than I thought I would, which is okay. Okay. So there's two phases in the XY model. in the original XY model. One where this r is greater than 0, and one where this r is less than 0. So that's the critical point at r equals 0. When r is greater than 0, this field psi is gapped. It has a finite mass. And what I'm interested in is the physics at energy scales small compared to that mass. And when I go to low energy scales, this massive particle doesn't enter into my thinking, right? It's like the W boson at ordinary everyday life. We don't have to worry about the W boson when we're talking about electromagnetism. So it decouples. And so when that happens, this entire Lagrangian essentially is 0. Okay, so there's nothing. There's no propagating degrees of freedom. There's no excitations unless you go to high energies of the order of the mass. And because the Lagrangian is 0, we can call that a vacuum, or otherwise we can call it an insulator. But when r is less than 0, this field condenses. The XY model condenses. It gets long-range order. It becomes a superfluid. And then the low energy fluctuations are the Goldstone modes associated with the XY model. Okay? So that has a form like this, where the phase degree of freedom couples to its derivative, and it couples to this background field A. And that's a superfluid. Okay? So the phase diagram looks like this. As a function of r, you have an insulator here and a superfluid on this side. But because we have a duality, we should be able to understand the phase diagram from the other point of view, the dual theory. So if we look at the vortex theory, lowercase psi, that's Lagrangian is here, when r is positive, r prime is positive, it also has two phases, I should say. One where r prime is positive and one where r prime is negative. When r prime is positive, again, this field psi is massive. You can ignore all of its effects. And the only thing that enters in this Lagrangian is this term here. And I've included the next correction to this, which involves the Maxwell term. It turns out that in 2 + 1 dimensions, the Maxwell term is irrelevant. So that's why it was not included here. But it will be important to include it here in this line. So the low energy action involves a fluctuating gauge field. This is roughly like E squared plus B squared, right? This is the Maxwell term. And this is the coupling of this, the fluctuating gauge field to the background. This turns out to be identical to the description of the Goldstone mode, okay, of 2 + 1 dimensional. So this is a 2 + 1 dimensional electrodynamic action, Maxwell action, but it turns out to be identical to the boson superfluid description. And I'll explain how that comes about. We can see it explicitly. But now look at the other phase. When r prime is less than 0, the field condenses. But now, since little a is a dynamical field, it gets gapped by the Higgs mechanism. Okay? So when this condenses, there's a Meissner effect for little a. It gets gapped, it gets pushed up. And again, like our philosophy of if we're interested in low energy physics, at energy small compared to the mass of the gauge boson, or alternatively, at length scales large compared to the penetration depth of the photon, there's no penetration of the photon. We can ignore it, and for all practical purposes, set it to 0. When you set it to 0, you get again, we can ignore all the fields. They're all gapped out. The photon 0 means that the Lagrangian is 0. So this encodes, when the ordered phase of the vortices encodes the insulating ground state. Let's talk about the disordered phase, where we have what looks like a Maxwell electrodynamics. What I'm going to tell you is that this is the boson superfluid. So if we look, let me first tell you the conclusion and then see how we can understand this. I told you that in the original representation, there's a superfluid and an insulator as a function of r. Now, as a function of r prime, there's also two phases, except that when r prime is negative, there's a Higgs mechanism. The Lagrangian is 0. That's the insulator of the original degrees of freedom. And when r prime is positive, we get a superfluid of the original degrees of freedom.
Question?
Yeah.
In this dual language, what does the confinement phase correspond to in terms of the original?
Confinement of little a?
Yeah.
Well, it's Higgsed. It's Higgsed, right?
But if it's not Higgs, then if I have
There might be some other.
there's another knob I can turn
Yeah.
to this dual theory, then what does it mean in the original?
It could be another. There could be a. I would think that there's only the Higgs type confinement. I'm not sure. Maybe some of you have comments on this. Right.
There's nothing I can change in the original theory to make the little a in the dual compact.
You would break. Exactly. Yeah.
So the
That's right.
which you break in term in the original theory would be the monopole operator.
That's right. Okay, so there's a phase diagram like this. Now let's try to understand why this is the Goldstone mode of the original XY model. So the XY model had an action like this, right? We can express its partition function using a Hubbard-Stratanovich field, which I'll call J. And those will be related to the current operators, okay? So you can see that if you integrate out J, you will get back the original Lagrangian. Okay? So this is just a Hubbard-Stratanovich identity. Okay? But instead of integrating out J to get back to the original, what we do is we integrate out theta. Okay? And this can be, by integrating by parts, the d mu acts on J. And so when you integrate out theta, this acts like a Lagrange multiplier, enforcing the constraint that partial mu J mu is 0. In other words, charge conservation is implemented explicitly. Okay? Now, since charge conservation is implemented, the way you deal with the constraint is a divergence-less vector field in 3 dimensions, or 2 + 1 dimensions, can be expressed as the curl of another. And so doing that, we plug it back in, we get this. So from this to this is an exact identity. Okay? This line here represents a propagating photon in 2 + 1 dimensions, and this line represents a Goldstone mode of the XY model in 2 + 1 dimensions. And they're the same thing. Okay, I guess I've completely run out of time, have I? Or
You need to move into equation session.
okay. I can stop now, and we can continue onwards. So, however you wish to proceed.
Model on honeycomb lattice. Initially, they have spin-spin interaction, and he did a transformation to Marana representation. So, do you consider this as duality?
You can put it this way. I think it's related to There've been studies where you can think of that mapping as a higher dimensional version of the Jordan-Wigner transformation.
Yes. So there are two methods. One is he doubled the Hamiltonian.
Right.
And then used Marana representation. And it turns out there's an infinite conserved quantity in each flag. And the other one is what you just said. It can transform compress the lattice so that one can define one-dimensional string.
Well, you're not really compressing it. You're just merely going.
Yeah.
You're going around.
But these two are two different transformations.
But they're equivalent. They lead you to the same end result.
Yes, but the conserved quantity are different, but somehow related.
Mm-hmm.
So first question is that duality?
It's a duality at the Hamiltonian level. Yes.
So it's not the duality like this?
Not to my knowledge.
And Lay can also define flux.
Yes.
Okay, you can think log model is dynamics of flux
Mm-hmm.
in the flux. So I see this spin and the vortex duality in this sense.
Well, we know that. There is a related duality, which is not exactly this, which is that the 2 + 1D Ising model, quantum Ising model, is dual to a Z2 gauge theory. But I guess you're not exactly referring to that, are you? This is just some exactly solvable model which can be solved by Majorana fermions.
Yes.
Yeah. So yeah, you could say it's a duality.
But that duality is not the duality here.
No, it's different because here we're talking about U1 conservation. There's always a conserved charge, a continuous theory like XY model. Yeah.
The boson-vortex duality.
Yeah.
If you take your original XY model Lagrangian and you put it on a curved manifold, does it go through like this as well? Or does it continue to work?
I would think so because the curvature is like a background, metric or something, and you can dualize the metric.
How does the metric dualize?
It's like a gauge field that lives on the links of the original lattice, and it has some dual representation in terms of the dual links. I'm not entirely sure, actually. Then that's not obvious to me.
It just unequally seems like maybe like epsilon j isn't necessarily like b epsilon j might not be 0, and so maybe then you can't define this a.
But if you have a conserved energy density, I think that couples to the background metric, right? So if you were interested in thermal conductivities or something like that, I think you would couple it to a background metric. So there is some conserved quantity that enters. Pardon me?
No, EJ equals 0 is fine, but B star j might not be 0, and then you might not be able to make a little a.
I'm not sure. Okay.
So hence metric also should be really important. Is there any problem when you, for example, work not in a plane but in a sphere, that the effects of boundaries are not well announced?
Not to my knowledge. Yeah. Yeah.
Till how many millimeters does the correlation length compute in the first part?
Computed?
Yes. Are they
You mean for which model? For which? Are you talking about experiments or model?
in the model?
Which model?
Like coming from data? The two correlation lengths you talked about.
Oh, I was talking about my own motivation. That's experiment, and one significant figure at best.
My question is about Duality transformation. So when we do this transformation, how does the topological phase transition and the fermionic model map to the spin?
So the fermions are already in the superconducting state. Okay, so the charge conservation has already been broken. And that makes sense because we were talking about the Ising model, which has only binary numbers. So the fermions cannot have a continuous charge. So that's why we have a superconducting state. It turns out what the two phases correspond to are one in which you have a BCS-like superconductor, P-wave superconductor, because it's spinless fermions. And on the other side, it's more like a BEC P-wave. So this is exactly the kind of thing that happens in 2 dimensions for P plus IP superconductor. But here it's 1D and it's a P-wave superconductor. And that turns out, like, unlike the S-wave case, there's a BCS to BEC crossover for S-wave. But for the P-wave case, there can be a transition exactly at the critical point when the Fermi points, there's a vanishing of a gap. And that's the transition associated with the 2D Ising model. Yes.
Give me a historical context. Like, one thing we learned, like, when Duality first proposed, basically the XY ability case when you presented here, like, what did that tell us? Like, when it was discovered?
What did it tell us?
Like, what has it used been for? Like?
Yeah, so it's been used in many. Okay, so it has a niche application in more exotic aspects of condensed matter physics. certain spin liquids and fractionalized phases of matter. But the one that I like the best is to think about the superfluid to insulator transition in, say, the first class of experiments that I was talking about. Many influential theoretical treatments were involving using this duality to study the universal properties of that transition. Okay. Yeah.
All right. One last question, and the long question and answer session is going to be tomorrow.
Okay, so I have a question regarding the duality between particle and vortex.
Yes.
So does this kind of duality depend on the underlying manifold that you are looking at? Like if you have a sphere or if you have a torus,
Okay.
different?
I mean, I think the only thing that you need is charge conservation and some U1 charge conservation. So I don't think the manifold really matters. There's no topological order or anything like that. There's no dependence on the genus or anything.